Hello learners, welcome back to my channel Shraddha's Physics. In this part we will see the stationary state, that is the time independent solution. So now let us begin our topic with the stationary state solution. So here you can see if the probability distribution function, that is psi star psi, the probability function this psi star psi for any wave function, that is suppose psi is a function of x, y, z and t, it is independent of time, then the state of the system is said to be stationary state. That is, when this state function, it will not depend on the time, in that case we can say this is a stationary state and we can calculate the probability distribution function. So here we can write, if the probability distribution, that is psi star psi for the state of the system described by the wave function psi, that is the psi is the function of x, y, z and t, is independent of time. It is independent, that is this wave function psi is independent of time, then the state of the system is called, or we can add, then the state of the system is said to be a stationary state, Okay, that is, in order to find a stationary state solution of the Schrodinger equation, we can apply the method of the separation of variable. So here let me write, in order to find out the stationary state solution, the stationary state solutions of Schrodinger equation, we apply the method of separation of variables. Okay. So the Schrodinger time dependent, let me write first, the Schrodinger time dependent wave equation, dependent wave equation is, so basically you can write, this is your h cap psi equal to E psi, where h cap is the Hermitian operator and E is the eigenvalue equation or the eigenvalue of the Hermitian operator h cap, okay, and psi is the eigenfunction. So here this h cap, that is this Hamiltonian, it can be written as equal to, this is your Hermitian operator, can be written as, this is the sum of the kinetic energy and the potential energy, and that is equal to, in place of kinetic energy, that is your kinetic energy operator and it is also your potential energy operator, and that is equal to, for the kinetic energy you can write minus h square by 2m delta square, and for the potential energy simply we can write, this is your V cap. So here I can write, or this h cap psi means this is your minus h cot square divided by 2m into delta square plus v whole into psi, that is equal to eigenvalue is your for the E operator, or we can write simply this is your I h cot dou by dou t into psi, because this is your total energy operator E and its value is I h cot dou by dou t. Okay. So here if the potential energy is independent of the time, so here if the potential energy is independent of time, and depends on the position only and depends on position only, then so here we can write this potential energy function, that is your, we can write, that is by applying the separation of variable method, we can write the wave function, that is psi of x y z t, that will be equal to f of x y z, that is one will depend totally on the space variable and another function which is depend on the time t. Okay, where this f of x y z, it is the independent of time, this function is independent of time, this is independent of time, and the function phi of t, that is equal to, so here this function is, we can say this is function of time. Okay, this is function of time. So the solution for this equation, that is this psi of xyz, it can also be written as, so the solution is the psi of xyzt, that will be equal to sum over n cn, the nth fn xyz and the exponential minus iota en t by h cot. Okay, that is for all the particle, we have simply written here the n. Okay, this n is for all the particles present here. So for a particle confined to a finite region, for a particle confined to a finite region, the function f of xyz, will be single valued, and it is also continuous, and finite only for certain definite values, only for the certain definite value of energy, Okay, so these allowed values of E, of E are called as the eigenvalues. They are called as the eigenvalues. And also here you may note that corresponding to each allowed value of E, corresponding to each allowed values of E, there will be one function, one function, that is f of xyz, one function f of xyz, and that is called as eigenfunction, called as the eigenfunction. So here you can see that when a particle is confined in a finite region, then this f of xyz, it is single value, continuous and finite. For the definite value of energy, that is here the En, when it has a value like E1, E2, E3 and so on. So in that case we can say this f of xyz, it will be single value, continuous and finite. Okay, and here this En, it represents the eigenvalue of the equation. Okay, this is the eigenvalue and that function is known as, this is your eigenfunction. Okay, so this is your eigenfunction which is single value and continuous and finite, and here this En here represents the eigenvalue. This is eigenfunction and this is your eigenvalue. So therefore we can write, so we have finite many solutions, finite but many solutions of Schrodinger equation, Schrodinger equation for time independent, potential energy V of x, y, z. Okay, that is, here we can write f1 xyz, and here the exponential minus iota E1 t by h cut, and f2 the function of x, y, z, and here exponential minus iota E2 t divided by h cut, and so on up to fn, that is the function of x, y, z, and here the exponential minus iota En t divided by h cut. Okay, so these are the solution of the Schrodinger equation. And also you may note here, for each of the solution, for each of these solutions, psi star psi is independent of time. It is independent of time, and hence these are the stationary state solution, solutions of Schrodinger equation, Okay, so basically the stationary state solution means it will not depend on the time, that is this function will independent of time, or you can simply say that here the potential energy will not depend on the time. So this is all for today. If you have any doubt, can ask me in the comment section. Thank you all.